So what we're going to be talking about first is we're going to be talking about how we find missing sides in right triangles. This seems to be the biggest issue, is figuring out which method we're going to be using. So we're talking about finding sides in right triangles. Finding sides in right triangles. There are two styles of ways we can do this, and it's based upon what we are given. If you're given one side, or if you're given two sides. If you are given two sides in a right triangle, it must be a right triangle, then we use the Pythagorean theorem. Which again is a squared plus b squared equals c squared. Does anyone remember what's so special about the letter C in the Pythagorean theorem? It definitely, thank you, Alidra. Yes, it is the hypotenuse. It must be the hypotenuse. Way to go. Thank you, Alidra. Now, we worked out a few examples of these. We'll look at an example of that in a little bit. The next thing we're going to look at is we're given one side. If you're given one side, we have two options. If you're given one side, there's two options. We're looking for special right triangles, but it is a possibility it's not going to be a special right triangle. What we look for is if we have a 30, 60, 30, 30, 60, 90 triangle, or we have a 45, 45, 90 triangle. It is a possibility it could be neither of these two. If it's not these two, we cannot move forward. You cannot solve. When you guys go into trig next year, or college algebra, you will be able to solve it. Remember, for a 45, 45, 90, we have this is a special right triangle with the following lengths. We know it's an isosceles right triangle, meaning the two sides are the same. And again, these two angles are both 45 and 45. The general lengths, does anyone remember the general lengths in a 45, 45, 90 triangle? Anybody? The general lengths in a 45, 45, 90 triangle would be 1, 1, and the square root of 2. Every 45, 45, 90 triangle is a model off of this one. It's either being expanded to that size or it's being shrunken down. Remember we talked about reductions, or we talked about like enhancing something, like a dilation. Every 45, 45, 90 will match up with this here. The 30, 60, 90 is a little bit more difficult because we have three sides we have to look at, or three different sides we have to look at. That's not bad drawing for this little tablet. Oh, definitely jinxed myself right there. Let's try that again. It's much more difficult than it looks. And you guys don't know bad. Here we go. Now what is very important here is for the 30, 60, 90. 30 and 60. Across from the 30, across from the 30 will always be 1 as our general length. Across from the 60 will always be the square root of 3. And then across from the 90 is always going to be 2. Every 30, 60, 90 triangle will be based off of this. It's either going to be an expansion of this or a reduction of this, like we talked about earlier. And the way we solve both of these types, is we use proportions. We're going to use proportions here. And we'll look at an example of all three of these in just 1 second. All right, so you guys can see in this example up here, where everyone's eyes are right now. Yeah. Everyone's eyes are up on the example. Now, what it says is we need to find the value of x and y. Give your answer in simplest radical form. The way we do this, we kind of talked about this a little bit last class. The first step that you do is you label the general lengths of the triangle. Looking at the diagram we just put up, what sides are going to be the 1, and the square root of 2? Yes, Sam, go ahead. Yes, Malik, go ahead.
Looks like the x will be 2.
The x will be the square root of 2. Square root of 2. Big difference.
The 8 will be the square root of 3.
This is what type of triangle is it? Right, and is it a 30, 60, 90 or a 45, 45, 90?
So that 8 will be a 1.
Excellent.
And the y will be a 1.
Excellent. Now, that's the first question we have to ask ourselves. First of all, they only gave us one side. So we're looking for special right triangles. That special right triangle being 45, 45, 90. So we wrote our general lengths. We have our 1, our square root of 2. Now we know that every 45, 45, 90 is a scale model of the 1, 1 square root of 2 triangle. So let's set up a proportion. Let's put the original on top, and then we're going to put the problem on the bottom. Problem on the bottom. So, for the original problem, notice, that's where we're going to be using our orange numbers here. We're going to be using these orange numbers. So, Malik, you told me what side goes with 1?
Wait, there's 2 1s.
Right, let's pick one.
Well, the same thing. 8.
8, right? We know that the 1 goes with the 8 right here. 1 goes with the 8 right here. That's why we have them right next to one another. Now, which variable would you guys like to solve for? We have a choice now. X sounds good to me. So, Malik, do you think you can help me set up this side of the proportion?
Sure.
Thank you.
2.
Square root of 2.
Square root of 2.
Uh-huh. And what goes on the bottom?
X or 1?
X. Notice these are grouped together. These are grouped together. These are grouped together. We know this is a scale model. It has to be some kind of expansion of the 1, 1 square root of 2 triangle. Notice again, one thing that you guys tend to be doing that seems to be done very, very well is make sure one of your fractions should have 2 numbers in it. We can't solve an equation that has 2 variables in it. Now, we cross multiply. X. 8 times the square root of 2. Now, that's the difference between 2 and the square root of 2. We cannot combine these two. They're not the same. It's going to be 8 times the square root of 2. The square root of 2 is not 4. 2 squared is 4. The square root of 2. Look, plug it in the calculator. Plug in the yellow calculator.
So 8 times 8, 64.
So x equals 8 square roots of 2. 8 square roots of 2, right? It's not going to be a whole number. And it's not 1 because 1 times 1 is 1. The square root of 2 is an irrational number, so it's just going to be a decimal, irrepeating decimal. So we've given, you guys can't simplify this. Things inside of square roots can't be simplified with things outside of square roots. So we're lucky x is just 8 square roots of 2. I'll write that up over here. We found our answer. Hold on 1 second, Sam. Let me write this down. 8 square roots of 2 is the value of x. All right, now, let's look at solving for y. So let's clear out our annotations and solve for y. Now, let's go over again the lengths for these right triangles. Any 45, 45, 90 triangle is going to have the same corresponding lengths. 1 for the leg, the other leg will be 1, and then the hypotenuse, that's known by what's across from the square root of, or across from the right angle, is always going to be the square root of 2. Always going to be the square root of 2. Now we need to solve for y. We already found out what x was. Let's set up a proportion for y. Let me at least, yeah, Sam, you can help me set up. Let's just, let me get this all together. Now we're going to put the original on top again. And then the problem, the numbers from the problem on the bottom, because we like to try and be systematic about it. All right, Sam, what do you think, dude?
So it would be 1/8, right?
Again, we would have, that's great, 1 over 8, because we're using this information again, 1 over 8.
Yeah. And then you have the 2 root of 2.
We just did, if we were solving for x, yes. We already solved for x.
Oh, we're solving
For y, yes, 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 yes.
Y is going to be 1.
Uh-huh.
It was y.
1 over y. Correct, thank you, Sam, that's perfect. Now we cross multiply again. We get 1, what's 1 times y?
We can't do that.
Oh, we can, it's just y. Anything times 1 is always itself. What is 1 times 8?
8.
Just like we illustrated for, it's going to be 8. So we get y equals 8. Now, there's a way we could have known that was going to be 8 before. Because this is a right isosceles triangle, we know that these two lengths are always going to be the same. In a 45, 45, 90 triangle, the legs will always be the same. Always be the same. Yes, Malik?
How can you tell the difference between
Isosceles.
isosceles triangle and a regular white triangle?
You have to see, if you see the 45, we know that both of the angles are the same. Therefore, both of the sides are going to be the same. The property of isosceles triangles. Great question. So, what we have here is we've found all the missing sides. Let's erase some of this so we have a little bit more space. We knew that the one leg, or our horizontal or vertical leg, was 8. We found out that the other leg was 8. We weren't surprised by this because we knew it's an isosceles triangle. We found out that the hypotenuse was 8 square roots of 2. Notice, this is almost exactly the same as our diagram that we worked on in our flow chart. Notice 1 square root of 2. Our example was 8 square root of 2. So you can see it holds these proportions. Now, not every example we do is going to be blank times the square root of 2 for the hypotenuse, but it gives us a general idea of what the shape is going to be like.